Hello, everybody. Welcome to the stream. We have an interesting one today, I hope. I had recommended last time that everyone go watch Freya's video about the continuity of splines. And I went and watched it again. And I'm really glad I did because it refreshed a lot of things in my mind that I'd learned the previous time. And so I think that there's some pretty clear opportunities for what we can do with splines in this library based on what I saw in that video. And the first thing is I need to clarify some terminology. The thing that's not, if you're using these spline functions in a very constrained sense, the thing that's not obvious is that the value for t in the parametric curve can go outside the bounds of 0 to 1. And at that point, you just have a curve, right? Like you can go to negative infinity and positive infinity with it. And so each segment with the control points that are relevant for that curve it defines a curve that has an infinite domain, right? So the reason why they're called splines is that they are the combination of multiple curves. So one direction we need to go, we're not going to necessarily get there today, but one direction we need to go is to the sequencing of different curves with overlapping knots or control points, and turning those into sequences of curves, right? So that's a spline. A spline is a sequence of parametric curves. And that's definitely what we wanted from the original plan, like the Catmull-ROM. I don't think I had a really good idea of how to construct it. But if we, especially on Bézier's, like Bézier, the de Castelliel method is really great for, a general solution to any order Bézier curve. But what, one thing that's not obvious, is that you don't need n-ary Bézier curves. You usually need linear or quadratic or cubic. People don't usually go beyond cubic. And the neat thing about cubic is that they are general over the lower order curves, right? For Bézier curves. So if you have P1 and P2 control points, at the same point, you basically have a quadratic. And then if P1 and P2 are actually on the line from P0 to P3, then you have a linear Bézier curve. It degenerates. So maybe you do a bit more computation when they're equal, or when they're on the line. But you can use cubic Béziers to represent those lower order curves, right? Okay, so what that says to me is that, for most applications, we're going to want cubic curves. The Catmull-ROM is cubic, right? The Bézier is cubic. All of them have, when I say cubic, all of them have a factor of t cubed, right? And then, factors on top of that, or added to that are t squared, t, and then constant. So what that, if you've done any linear algebra in the past, you've done systems of equations, this, hi NNB, welcome. This looks like matrix multiplication, and there's a great form of that, of matrix multiplication for these curves. So let's switch over to my screen here. I have pulled up some lecture notes here on the right from a university course about splines, about curves, parametric curves. And it's talking about the ones that we care about. So the form of a cubic Bezier curve in matrix form is you have this 4x4 matrix with these coefficients that are static. So this is a really good advantage for us in that we can say, yeah, we're going to make this, this is like constant for all cubic Bezier splines. And then the thing that it gets really interesting about that is all we have to compute when we want to sample the curve at a particular time is, you know, the powers of t. Here they're using u. So let's say I wanted t at 0.5. This vector on the front is 1.5, 0.25, 0.125. The thing I like about this website is you can change the size of the matrices, and like it'll show you how matrix multiplication works. So if we hit multiply, it's going to take that matrix and flip it on its side. So we're basically doing columns at a time. And then it's the dot product of this vec4 with this vec4. So we do that. There's our first factor and our second factor and our third factor and our fourth factor and so forth. And so these become the coefficients or the scales of the points, of the control points. So then what we would do to find P of U is, I don't know what these like random characters are out here. You would take this multiplication, this, you know, 1t squared t cubed times this matrix, and that gives you these, and then you multiply it by multiply these coefficients by the points. So this is a, you know, a straight, actually I guess you could do a dot product again, but these are going to be, you know, 2 or 3 dimensional points, so it's really more of a scale. So you take these factors, scale the individual points, and then sum them up, and that gives you the point on the curve. So I think the neat thing about this is, especially for Bezier curves, is actually about the same number of operations as the de Castelnau method. But what we have in here, I think, is like fewer conceptual operations, and we won't need to do the recursive method on that. Okay, so they talk about Hermite curves. If we go down here, and they're talking about continuity, go watch Freya's video. It's really awesome. But see, then we can also have this characteristic matrix for a Catmull-Rom spline. So where we say, you know, this is S in their thing, it's 1/2 is the alpha in the original Catmull-Rom, right? That we implemented the other day. So if we take, so here again, we can do a 4x4 matrix, and that completely characterizes the Catmull-Rom spline. And then we can compute it the same way. So this is like a really nice way to formulate it. And then the other thing that we can do is, I don't know why in particular they did it the 1/6 out front. You can do 1/6 across these coefficients and you'd be fine. But whatever. So then we can do B-splines. If you're not familiar with B-splines are used in all kinds of designs, specifically industrial designs, where you want higher levels of both, what do they call it? Both parametric continuity and geometric continuity. And I think Freya's video does a great discussion about why B-splines are useful in the when you're trying to draw a 3D figure. There's these sorts of points where it would look like a physical edge, right? Even though they're, you know, it's parametrically continuous. If you ran those up against one another, you would see like the pattern in a reflection change, for instance. So B-splines are really good at making those smooth curves that don't exhibit that property. and we'll want to make use of these. The other thing about them is because they have so many different kinds of continuity, they're really good for camera movement. The flip side of it is that B-splines don't interpolate the points. So if you specify the control points for a B-spline, it is very likely not going to pass through those points. Anyway, so there's a lot in here. Note how they're talking about subdivision. This is about like approximating a continuous function with linear segments, basically. So here they're kind of showing how you could take a something that's defined by some splines and then subdivide it until you have enough detail such that it looks smooth in a 3D environment. And that a lot of that is just taste. But they're talking about the technique there. So what I want to do today, I got started yesterday on a matrix library, and basically I'm porting the matrices from Gleam, which is the Rust graphical mathematics library. Very popular, partly because most of the data types are a copy. They have const constructors, and there's also a lot of like really useful operations on them. So if you're doing CPU side stuff, the other thing is that particular ones, for example, they have some byte aligned, or not byte aligned, like word aligned versions of, say, a 3x3 matrices and vectors, such that they will occupy like even amounts of space. That's really useful when you're sending things to a graphics card, so that like you wouldn't, you send a vec3, you're going to have a wasted word because they're going to pad it to a vec4 so that it's aligned with RAM. Anyway, we don't actually, on the Gleam side, we don't care about alignment really. We don't have to deal with that. So what I'm going to do is I'm going to show you what I have so far. So here's our Splines library, which we pinned up last time. And here's the matrix library I started. This is just an example. I'm calling it matx. Maybe I'll make it matrix-gleam, sort of like I did easings. But the idea is similar to the vec library. Thank you, NNB. We'll call the namespace matrix, and then you'll have like mat3f. Now I'm not planning to do, because like this is very focused on the mathematics and not like vex as a matrices as a generic data structure. I'm not going to necessarily expose generic forms of these. I just want to do the float ones, and then if people want integer ones, it'll be mostly a matter of copy pasta. Okay. Let me show you what I did. So mat3f is not complete. Let's look at mat2. I made the definition of this really simple. It's a vec2 of vec2s with floats. Thank you for that type alias. Yay. Very happy. Define some constants. Some of these are public, some of them are not. The zero constant is obviously, a full zero matrix. Then this is, I was actually surprised to find this was not in the vec2f library, this constant, x and y. It is in Gleam though. So I just defined local constants for that. And then that would be basically like if you multiplied, so the x normal and the y normal vector, basically. And if you multiplied some other vec2 by the x normal, you'd get only out the x factor, and so forth. Okay. And so then identity is just, the x and then the y. Now these are column major, I think is important to say. Conceptually, that can be a little bit hard to think about at times because we're used to thinking of like, top to bottom. But if you go left to right, it makes certain forms of the math really easy. And we'll see this down here. So for example, let's go down. What's a good example? Maybe this is not as good. Oh, right. So, it's probably not as obvious in the Mat2 one. But I've implemented a lot of the functions that, especially the constructors, that Gleam has for its Mat2. I'm trying to find one that's really good. So example here maybe is that you remember over here, you note that when we multiply this vector on the left, so this 1x4 matrix basically on the left, with this 4x4, what happens is they kind of turn it on its side and then do column by column. So this, 1 times 1 plus 0.5 times -3 plus 0.25 times 3, and sorry, that's really small, plus 0.13 times -1. That's the dot product of this row vector with the first column. And so if we do column major and we want to do this sort of multiplication on the left of a row vector, then that falls out really nicely. You say I-axis dot x of this matrix, and say this is dot y dot z dot w, and then do the dot product, and then that becomes the first output. And then you continue to do dot y times the row and dot and so forth, and then and that's what you get. So that's why column major rather than row major. Row major is easier to think of. It's easier to turn, a list of lists into that. But if we do column major, we get some mathematical properties that are pretty nice. Okay. So, that's, Mat2F is complete. Mat3F is not. We'll come back to it, I think. But I want to do Mat4 today. And I apologize, this is probably not going to be as interesting because it's mostly porting Gleam. So let's look at how they do matrix 4s. So similar to what I did in Mat2F and Mat3F. Yeah, naming them is hard. Like you could say x-axis, y-axis, z-axis, so forth. But yeah, it's okay. Okay. The thing that I think is going to be hard in general with Gleam is making one that's generic over any number of entries. There are just too many. Like we don't have const generics, so you can't say a number like an integer, non-negative integer is a generic value into a type, not like you can in Rust and some other things. We are not making a generic matrix library, I think is what I mean to say here. We're making one that's specific to these n dimensions, and they're all floats because that's what we're going to do in graphics. Okay, yeah, I'm just going to copy paste some of this and we'll get going. Okay, so we're gonna need vec4 and vec4f. We're gonna need vec4f, and we're already importing those. Okay, so Oh, and I still, this is a 3 by 3. Didn't fix that. Okay, so we're going to do something similar to this. And we're going to say mat 4F. And that's a 4 by 4 column major matrix of floats. Back 4, back 4F. And yeah, generic matrix is quite something. I'm not even sure how you'd do that. Yeah, I think that, like, at that point you're talking tensors, at which point you should be using something else. We care about the ones that are relevant for 2D and 3D graphics, so this is where we are. Okay. So, you know, this has 16 spots in it. We could do a constructor like this, but I'd rather do a constructor like this. So let's go ahead and copy and modify that. And map 4F from its 4 columns. Okay. And we'll change those to vec4F in a second. Vec4D. Okay, so I don't know if y'all can hear it, but my cat is over here snoring. Okay. And this is Y and Z. Okay, so this is, you know, I could have called this X, Y, but that gets confusing. If these are named differently, then it's a little bit easier. Okay, so mat4F, and it hasn't registered that this thing is in the server, in the language server yet, so nope. Vec3F, I'm going to replace that with Vec4F. Okay. Okay, so this is the main constructor that we'll make use of. I'm going to go back up here to the top. There are some other useful constructors, mostly that come from, I mean, you can do this. Like, I hate this, though. This is awful. But let's go ahead and define the other constants. So this should be straightforward. And this is, you know, just really easy stuff. We'll repeat some of these things that we did in the other modules. But you can see there that that's a real straightforward one. So I'm going to copy, oops. Yeah, that's fine. It can be up there. I'm going to copy these constants, and then we'll extend them and make one for W for now. And maybe I'm going to change these all, of course. Let's do 4F. Okay, and then I need to get these on lines together. Unfortunately, the formatter puts them on separate lines. And then here, okay. So now we have the unit vectors for each of the axes. And now we can define our public constant. Vec4 X, Y, Z, W. This will be useful I think in this needs to be pub. This would be useful in tests, for example. So like here in the README, I gave an example of, hey, take any vec3 and then multiply the mat3f identity by that vec3, and you should get back the same vector. That's basically what we're going to do here. We can use that in tests and so forth. Okay, I don't think it's useful to go all nans. I don't know why you would do that. I don't remember why this exists in Gleam. But maybe what we can do potentially is do this. And I want to make this a little bit more clear. Like so. That's quite a bit better. Then it makes clear that, this is accessing those fields. It's actually just wrapping it up. Right? Okay. Okay, so we have from columns. We don't need these things that have to do with arrays. Gleam doesn't have fixed size arrays or slices in the same sense, so we're not going to bother with that. From diagonal is useful. And this one is what I might consider using the spread out version, right? Okay. Literally copying. Okay. So from diagonal, and the diagonal is a vec4f. This is mat4f. Now, the other thing that we can do is just say from columns. We could also, I was going to say we could multiply, but that's going to produce a vec4. And what we want is the matrix. Okay. Well, let's just do it. We'll say from columns, and we're going to say this is going to be diagonal.x 0 0 0, and we'll do this and move things around. Diagonal.y. Diagonal.z. Diagonal.w. Okay, that's not so bad. Thank you, formatter. Also, I like this form because you can really see it going along the diagonal there. Visually, that makes me feel good. And it's not any more expensive than splaying it out and then constructing the vec4s separately. So, okay, we don't care about quaternions yet. From scale rotation translation would be really useful. Not going to bother with that yet. What I want to get to is just the primary arithmetic things with matrix multiplication explicitly. Maybe scaling by a float. Yeah, from Euler's. Yeah, so like these mat4, mat3 can be used as a transformation matrix in 2D. Mat4 would be useful in 4D or in 3D. If you need more than just rotation, obviously quaternions are better for rotation. They're a little bit more efficient, both space-wise and probably computation-wise. Now, I did in Mat3 make a from contorting. I ported that. But yeah, so let's go ahead and do the transpose, which should be straightforward. Mat 4F along the diagonal. And this is going to be a little bit mechanical in all these, but that's okay. Because what we want to get to is doing the interesting spline implementation with these mat 4s. Okay, so what are we going to do here? Let's say from calls. And we need, so this is basically the column. The X column becomes the X row. So we could say X, Y.X, Z.X, W.X. So column major means that it goes down. So this is the column becomes the row and vice versa. And this is X.Y, Y.Y, Z.Y, W.Y. And we'll repeat that, and I'll just do, these are Z and W. Okay. Transposition was easy. Okay, they're doing from rotation, from scale. That might be useful. Don't actually care yet. Well, we can make that a to-do. It's accessing specific columns. There's the transpose. Yeah, so we did it basically exactly how they did it. Okay, so we could get the diagonal. Okay. All right, so then we'll do vec4f, mat.x.x, mat.y.y, mat.z.z, mat.w.w. Okay. The determinant will be very useful because we're going to have to be able to do inverses probably. So let's implement the determinant. This one is going to be a little bit not fun. But what we can do returns the determinant of the mat4f. Okay. And this will be a float. So they're looking at, they're labeling it like this. I don't really feel like we need to extract those. But we could do, it would make doing this a lot easier. God, look at those awful variable names. Here, let's do this, and we're just gonna, you know, it's not valid Gleam. But what we can do is we can say, do like this. Okay, let's get it lined up. And let's do modify. Okay. And now we can go here and we can say this is vec4 x, oops, y, z, w. Okay. And then now, with a little bit more modification, we can make this pretty simple. Yep. Because this is vec4f as a mat type, the veclib is somewhat a generic. Yeah, somewhat. There are aspects of this that are, yeah. I mean, your vec library is generic over the elements of the vector, like the components of the vector, right? So we've got the opportunity there to do some things that are pretty interesting, I think. Let me get these lined up so that I can start to modify all of these operators. And the problem is this needs to be braces, not parens. So let's just go do this first one. The nice thing about this being implemented in Rust is there's a lot of syntax similarities, so I just need to copy and modify. Oops. And then we'll dot, 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 and then, oops. Okay, so that doesn't look nice. But it's fine. And we can be pretty confident that that is correct because we copied and modified. Yeah. Okay, so the inverse, what I did, and I'm really finding this vertical split annoying. What I did for mat2 was the inverse returns a result. So if and the reason it has to return a result is float divide is, the 1 over the determinant. If the determinant is 0 or close enough to 0, this is going to return an error. So we can I don't really like the way that they did that, but that's interesting. Obviously, computing the inverse of a 4x4 matrix is a lot more complicated than a 2x2. All right, so we got the determinant. And they do some weird stuff with like const generics. This is the sort of thing that we'll be doing. But let's go ahead and make that similar to this. Except it's not going to look like that. This is, this is different. Just want that comment. Here, we can hide the project browser. There we go. Get a little bit more space. Okay. So if we take this, this is going to return a result of a mat4f or nil as the error. I think that given that there's only one kind of error from this computation, we don't need to be really careful about defining an error type here. So we're going to use the where's the determinant pulled in? Interesting that they're doing this very differently than they do the you know, this is literally the determinant here. Same computations, right? I wonder why it's implemented like that versus check the determinant. Let's comment this out for now. I feel like we need this, but I'm concerned about it not generalizing in higher dimensions. Because there's some business going on here that maybe it's like an efficiency thing. And we could reverse engineer how the determinant factors into all of this, but all right. All sorts of view matrices. Frustrums. Okay, what I want to get to down here is the simple operations like the implementations of mul. Okay, so this is transforming a vector. We did that in mat2. Yeah, so this mul transpose vec2. We can do the same thing here. But let's do this, right? Okay, so what did I call it over here? Mul vec2. So we'll say mul vec4. And I'm just going to delete all that for now. We'll figure it out later. Transforms a 4D vector. And this is basically the same thing as this matrix multiplication that we animated earlier, right? This is the key operation that we need. Okay, the thing is this mul is defined in terms of dot product. So what we can do is we can just construct it as a vec4. No. This is more the transformation. And this is the traditional like matrix multiplication. So this is basically what we'll do is we will say mat dot x, and we'll say vec for f multiply. Or this is scale, right? And then we're going to pass that to vec for f add. And we'll do this scale thing again. Mat y, RHS.y, and so forth. We'll duplicate that, z, w, w. Okay. Now we can do this mole transpose. Oops. Mole transpose vec 4. And this one is the easier dot product formulation. So we can do vec 4 here. Vec 4f dot mat dot x RHS, and just repeat that. CW. Okay. I'm going to say this explicitly because this is how I'm thinking about it. Equivalent to a matrix multiplication where the vector is on the left. And this one could be useful if we wanted to apply the matrix to the points. Except the points have more than one dimension. Never mind. Like actually, you know, in our formulation of the Bezier curve, these are points, 2D or 3D points, right? So that would be like a vec 4 of vec 2s or vec 3s. Does not compute. Not the same. We can, the thing is though, if we're doing this operation first, basically multiplying the vector of t values by the 4x4 matrix, then we come out with, you know, this vec 4 at the end, and then we can do piecewise multiplication. You know, it's similar to a dot product, right? But we'll probably use like map 2, for example. Or is it map 3? I forget. But there's a map function where you can take the components and map the pairs of them together. Okay. Yeah, so let's look back. Let's look at the Glam source again and see if there's anything else that we need. Obviously, this business is like they're using the traits to implement multiply and add, and we'll probably want to do those. I think scale is worth it. Because we'll probably we're gonna need that. Like I think that we'll want to use the matrix coefficients for B splines. They have a 1/6 factor on them, so it is a question of, do we apply that to the T vector, or do we apply it to the characteristic matrix? Kind of, you know, they're commutative because it's scalar, so it doesn't actually matter, but Depends on if we want to be pure or not in some senses. Okay, so this one is easy. Scale. And this is going to return a map4f. And this is basically from columns. And we'll do vec4f scale. And my language server is not happy. It is not giving me any suggestions here. And let's just do a lot of repetition here. Okay. This one, I think I implemented on the others. Yeah, you see now we're getting into trait. Trait implementations. You know, the generic parameter here is defaults to self. So, all right, let's just do the add real quick. Okay, I'm gonna get better docs eventually. We'll say A add4f, B map4f. And this is basically going to be this business again. Add a b, a.x, b.x. We can do this business again. Y, z, w. I love how this is composable. Thank you, NMB, for making that library so nice. Saves me a lot of pain. I guess we can implement subtract. It's basically going to be this. Yeah, see, it's not even complaining about these being the same name. Divide gets interesting. You know, multiply, I think, let's see how they implement mul. Right, so this is column-wise multiplication, which makes sense. So that's essentially like pairwise, like component-wise. I wonder if that's actually correct. All this code can be even shorter. Oh yeah, I could do map, right? Map 2. Okay, so let's try that. We could do vec4. The problem with my language servers is not happy, and it has to do with this business. Like my mat3f module just is not correct. So I'm gonna comment it all out for now, and hopefully make the language server happier. So you can say map2. There we go. Yeah, this is great. So map2 takes two vectors and a binary function. Okay, so we can say a and b vec4f dot subtract, right? That's it. Yay! Yeah, woohoo! Okay, so that we can do the same with this. Vec4 map2 a b vec4f add. Thank you so much. Vec4 map2 a b. No, it's just map. A is mat. Right, and here we'll put the scale in. Vec4f scale. Sweet. Oh my gosh, you're saving me. This needs splat. You could, yeah. I mean, I could do that, or just create the anonymous function like that, I guess. Is there something wrong with that? My way's better? Okay. Yeah, I was thinking with this one, you pay the cost for an anonymous function, but is it less than doing a splat? And then, yeah, I don't know. Yeah, so this one is interesting. Let's look at the vec docs. Because I think that we might be able to even generalize that, right? Because we want to scale each of the contained vectors. Is there a to list? Yep, there's to list. I don't know if this is more efficient, but I'm not using an agent to code for me, no. This is not, I'm not just trying to produce a library. I'm also trying to learn and share my learning with others. So that's why at the moment I choose not to use an AI agent. I have used them at work. They're pretty useful. Okay, so let's say map on this. And then we're going to do, let's set it up as a pipeline. That'll be nice. We're going to map with vec4f scale. Oh, do I need to do... That's not exactly right. Maybe I'll leave this for now and think about how to refactor it later. Because I want to take the... thing is, these are both... This would be map 2, wouldn't it? And then scale is the function. Or vec4.map2. And then, so this is going to return, yeah. Vec4f sum. Yeah, I was thinking I would do to list and then sum. I don't know if that's better. The problem is constructing the list, the additional list. I guess it's okay. little typos there. Okay, and these, how did I not get those? I must have hit, how did I leave these? I must have hit undo at some point and not noticed. Okay. Right, that's pretty good. I like that formulation. Thank you, NNB. That is wonderful. Okay. You know, divide is just scale with the reciprocal for floats. So, yeah. Lots of, okay, so that's sort of the end. We didn't implement inverse, so we can't implement divide. But this is enough. Yeah, okay, let's fix these warnings. We don't need those yet. We'll come back and add some stuff. This is enough in order to make our splines using the characteristic matrix. So that's going to be pretty great. Okay. So let's, for now, I'm not going to, I'm struggling with the name of this library. I would love to make it something. I initialized it with matx because that was not taken on hex pn. I would love to call it matrix, but there's an Elixir library called matrix on hex. So maybe what we do is we call it matrix Gleam. But for now, what we can do is bring our splines back up here. And I'm going to say we're going to use a path for now. This is not publishable. We'll fix it. Okay. We'll fix it later. So let's go and do Bézier's first because they're probably the simplest formulation. Yes, there's. Okay, so here's a bit where I need to update. Just update. Yeah, I think I need to, the constraints are, I need to say 2.0, 3.2.0. And just make sure that Gleam build still builds. Okay. Yeah, I know. Okay, I can remove that module. But what we'll do is leave it for now. Could you take a look at the PR on the easings package? Oh, sure. We can look at the PR on the easings. That's a good use of time. Oh, whoa. GitHub, Sean Cribbs. And easings. Sorry, that was really big. Big design and redesign and improvement. Oh, okay. I like that. Add to reverse symmetry functions. Okay, rename the file from easings to just ease. Shorter. Taste my own medicine. There are no modules named ease, so this is... I will not be conflict with anything. Okay. Like that. Bounce is a especially hard one to visualize. Okay, this is big. I may not have enough time on this stream to do this because I want to... I'm just going to hide the snapshots and assume they're correct. That looks a bit messy. Not sure. That doesn't actually look correct. It should bounce here, go up to the middle, and then bounce here. It looks like it's bouncing in the middle. That's not correct. Unless that's just floating point error in the middle, but it looks like it's bouncing in the middle. All right. I don't... If that's a thing where you're doing out and then in rather than in and then out, I don't know how that is actually useful for animation. Like, yeah, mathematically it's fine. Well, I mean, some of it is that here. But this one actually looks a little bit more like continuous. But okay, at least you got the numbers there as well with the representation. Okay, I'm gonna pause on this because what I want to look at is the actual code. Rather than, yeah, I'll do this after stream potentially this evening. Yeah, I'm sure it's fine on the IDE, like, but that's a lot of snapshots to look at right now. So thank you. I will have a look at this later, but after the stream. Thank you for that. Okay, so I want to say Bezier's, but let's look at Catmull-ROM, because if we look at this, the interesting thing is we don't need to do that algorithm that computes the knot intervals. And we don't need to do this way of sampling, right? Because we're not concerned with that. What we can do is do this. Right? And we can say the characteristic matrix, and this is where we probably need to do that, because it is just a type alias. It doesn't have its own constructor per se. I guess we could do, yeah, like there's this doesn't expose a constructor. It's just an alias for that. So what we can do, and Gleam will make sure that we do this correctly, but we can go back here to this business, and where's the Catmull-ROM? Okay, so it has a factor 1/2 on its t. So we can apply that here, or we can just do these parameters and then apply it later, which is fine. Okay, so we have 0, -1, 2, -1. Remember, we need to go down the columns. Okay, and then we have, I'm sorry for the flashing back and forth with it bright and dark. I'm really sorry. Let's see, the copying this is not going to go well. But yeah, that did not go well at all. Brutal. Okay. So 2, 0, -5, 3. 2, 0, -5, 3. And we'll fix those with adding dots to them later. And we have 0, 1, 4, -3. 0, 1, 4, -3. And then 0, 0, -1, 1. Okay, so we just need to put dots on those and then let the formatter go for it. Okay, so there's our characteristic matrix, which interestingly means that we can get rid of the knots. And the other interesting thing is we don't need an interpolator anymore, right? What we need is we need a way to it's a scalar, right? This is going to be a function of a and float to a. So scalar here is going to be vec2f scale. Because what we want to do is take each of the we want to do this computation, the front half or front 2/3 of it, and then apply that vector to each of the points. Okay, we're gonna figure this out. Interestingly, this could also and probably should be, rather than this, it should be a vec4. So we're going to say this is a vec4 of A. Yeah, and we need to import type vec4 as well. Okay, and then let's do the same for 3D. This is vec4. We don't need to compute the K, the knots. And the scalar is going to be vec3f scale. So much easier. Okay, so now we get to the thing is you can sample beyond t from 0 to 1. Okay, so we're going to get rid of remap. Doesn't need to exist anymore. What we care about is let's do our tvec is going to be a vec4 of 1, t, t times t, and t times t times t. Okay, so that's our input. And then we scale that by 1/2. So we're going to do t vec vec 2f or vec 4f scale by 0.5. Right, so we're multiplying 1/2 across that. And then we're going to go mat 4f mul transpose vec 4. And this is going to be characteristic, and we'll pass the t vec into the right hand side. Okay. And now that's going to output this times this times this, right? So basically, let's do the demonstration here, right? So let's go. Will you reset? Okay. 0, 2, 0, 0, -1, 0, 1, 0, 2, -5, 4, -1, -1, 3, -3, 1. Okay, so that's catmull rom. So now, since we're multiplying by 1/2 out on front, we can just divide each of these things by half. So let's assume we're sampling it halfway through. 1, 2, 5, and this. Like 65. Is that right? Okay. So multiply, and let's, this is just going to go to the end. So this is what our things times our points would look like. Pretty interesting looking, actually. Okay, so if we do that, then we want to do this is going to be we're going to vec 4 map 2 because we have a vec 4 of the coefficients and we have a vec 4 points. So we're going to do curve dot points. Okay. Okay, what is the type of this? This is a vec 4 of B, whatever B is. Okay, so this is... So I need to import vec 4f. Don't need lerp. Very nice. Okay. So... Oh, right. So I need to do the default is to go into the middle one, but we're going, yeah, so that's vec 4 float. So then I get a vec 4 of A, right? And then I need to do, so the other thing here is that we need something that defines what the sum function is. So why don't we rename this to scale? Are you going to work for me? let's comment this out for now and then see if we can get it to do rename. It really does not want to. We also need some. So this is going to be, sum is going to be a function of list of A to A. So here we need okay. Now we have everything we need. Okay, so then we'll say vec4 to list, and then curve.sum. Woo! All right, curve.scale. I like this formulation. Let's inline that, the t. So I would love to put this formulation in text here. But I think that what we can do is see if this even works. Why does it say it's not imported? There's no requirement that the package have modules in it that are named the same. Okay. Oh, helps if I'm interesting. I think I have a problem with dependencies being too. Oh, by the way, I can remove these. Don't need those anymore. Again, this may not be as useful. And you know, it was a good reason why I made this library 0.1, because this API is changing. So, what's wrong? Is it really just that it can't find that? How did I formulate it here? Yeah. It seems like we have no problem building that, but those are the same types. Okay, so now, again, oh yeah, so we don't need that type. that should resolve that. Okay, lerp, what's wrong? Are you okay there? Oh, I think it could be that the manifest needs to be updated, so it's not. Yeah, see there, it's like upgrading a bunch of business. Okay, now it's going. Got some warnings, that's fine. But if we go localhost, okay, so there's our catmull ROM, and that's using. What we can do here is, just to be sure, we can clean the build directory and then build it all. And refresh. And that is using our matrix formulation rather than the formulation we had before. So at the very least, I feel confident that that's correct. So let's do the same with Bézier's. All right. Pretty sweet. Can the dots have more distant? What do you mean? I want to see a longer curve. Yeah. Actually, what we want to do is probably make more points. Yeah. Yeah. It is a bit small on this, but it shows pretty distinctly the difference between a Bézier and a catmull ROM, right? This eventually would go through this point if we have another point out here and we extend it with the spline. So yeah. But let's go ahead and do the Bézier implementation. Okay, so again, we need to think about, it's going to be basically this same formulation because we're going to do the same computation. So what we can do, copy this, and let's go down here, and we're going to replace, and we're going to get a lot. So this the problem with how I originally formulated this Bézier is it's NR8. And I want to change it to be cubic. The other possibility is we could do it that way. Let's say this is cubic Bézier. And maybe we make it opaque. Kind of Bézier curve. Okay, so here we're going to say points is going to be a vec4 A, right? And then we need those scale and sum. So scale is going to be a function of a float to A, and sum is going to be a function of list of A to A. And we need to import vec4, type vec4. And I think that we're going to have to import a lot of the same things we did here. Let's just copy those and make sure that they're in here. Okay, so now what we can do is if we have cubic Bezier, and here we can say this is going to be points. Hello? Then this will just do to Castellio, right? Because points and interpolator and T. Because that's generic. But for the cubic Bezier, which is going to have points, scale, and sum, what we'll do okay, so this will be, we don't need this 0.5, right? But we do need the characteristic matrix. And we'll remove the qualification of curve, scale, and sum. Okay, so we need to import matrix mat4f and also type mat4f. And then we need to define the constant characteristic matrix like we did in catmull-rum. And then maybe before the day is over, we can implement B-splines using this. So the characteristic for Beziers is this. So we need 1, 0, 0, 0. I'm sorry, no, that's wrong. 1, -3, 3, 1, right? Because it's the column. And then -3, I'm sorry, 0, 3, -6, 3. 0, 3, -6, 3. And then we'll change the constructors as well. 0, 0, 3, -3. 0, 0, 3, -3. Notice how some of those stay the same. And all zeros in 1. Okay. So if we go in our new 2D, let's do a case list.length of points. If it's 3, no, if it's 4, right? And then we'll do cubic Bezier points. Is there an easy way to do vec for? The other way that we can do it is a match. Yeah, let's do points. And let's do a list match x. So this would be P0, P1. Actually, we just say X, Y, Z, W. And then we'll say points is vec for X, Y, Z, W. Although that's not really what they are. And then the scale is going to be vec2f scale. And the sum is going to be vec2f sum. For anything else, we're going to do this one. Okay. And then we'll do the same down here, right? So let's just copy and modify. Love that it's telling me the things to change. Yay, type systems. Okay, so maybe we don't need to keep the generic one around, but cubic is a special enough case and the most common in that the right. Okay. So I'll need to add something about, hey, if you're going to give us 4 points, then we're going to treat that as a cubic, right? I'm gonna put star here. Use and you pass 4 points. The optimized or sampling of this variant will use the matrix multiplication formulation instead of the Castellios method. Okay. All right. What's the warning? Oh, I guess not. Why not? All right, because we're not using it directly. Okay. All right, so that's pretty nice. And now we can do Hermite splines. But I think I want to do beast splines. Because here's their characteristic. The interesting thing, too, about this matrix formulation is you can go, and it took me a while to understand. I had to rewatch, of course, Freya's video, but if you go and watch that, I think you'll find this interesting. If you multiply the right-hand side, so if you multiply this 4x4 matrix by the points, you get the basis functions. The basis functions are basically how, at any point from 0 to 1, or even beyond, how much does each point affect the position of the curve? Each knot is the correct term for it. So you can see here that, like, at the beginning, the they keep using different numbering schemes. I wish they were more consistent. But you can see B1 for the B spline starts at 1/6, and B2 has an influence of 4/6, essentially. And then as you move to the right, B1's influence decreases and B4's starts to come up. But B2 and B3 are the most influential over the position, right? And then, like, how do you compute their thing? Like, each one of these is a curve. It's a cubic curve. And that's a way to understand the basis functions. How much does each point on the spline, or in the spline definition, influence the output? That's a pretty neat way to think of it. They're useful for analysis, not really useful for computation, actually. But that's a way to show, hey, this is the formulation of how each of these points affects position based on t, or u in this version. Okay, so now what I want to do is, just for paranoid's sake, we're gonna recompile it, compiled splines, and let's make sure that our Bezier still works and looks right. Okay, it is not right. Okay, I probably got the characteristic matrix wrong. Yeah, because it should be going, it should look like it did before, but it does not. And I actually want to rename these P0. P1. Just to be clear. P2. P3. And I'll do the same thing here. Just so we're not confused about that versus X, Y, Z, because they're not really X, Y, Z. Okay, so let's look at, I probably got the formulation of that wrong somehow. So the matrix formulation of, let's make sure our characteristic is correct. 1, -3, 3, -1. There's the problem. That needs to be -1. 0, 3, -6, 3. Okay. 0, 0, 3, -3. And okay, so that'll probably fix it. Let's see if our showcase will work now. No, it's still incorrect. So I've got something wrong there. It's interesting that our Catmull ROM was correct. Okay, so we create the cube coefficients, or the cubic formula for t. And we're multiplying by the transpose. Is that the issue? No. No. Because that is dot product, which is exactly what we want. And those become the factors that go into scale, right? I wonder what we messed up. Okay, so let's reset this. And so we're going to do 1, 0.5, 0.25, 0.125. That gives us our regular if we're at sampling at 0.5. If we do 1, 0, 0, 0, -3, 3, 0, 0, 3, -6, 3, 0, -1, 3, -3, 1. Okay, so this would make this column dot product with this column dot product, this column, right? So what we could do is let's do a little bit of a test here. And that's probably the right way to do this. Let's make a folder, Splines, Bezier test. And this should be a really simple thing to test. Right, that's fine. Bezier, cubic Bezier test. Let's call it that. Okay. And that should fail, yeah. Okay. So what we can do is let's construct a we need to construct something such that we can tell what the value should be really easily. And maybe there's an example that we can make use of. The other thing that we could do is say, what we want is for any arbitrary set of points that the de Castillo method is equivalent to the cubic method, right? That's probably a good way to do it because we know that the de Castillo method works. So let's we made this open, right? It's not opaque. So we can do this version. Like we can construct this. So we want new 2D and then the Bezier constructor. And then let's import splines, lerp2. That should be good enough. Okay, so we're going to say our cubic is going to be a new 2D. And we're going to give it vec2. We don't need the type, we just need the constructor. Okay, so we're going to say, we could use the things from our showcase example, right? That's not a big deal. Let's use these points. Okay. Okay, so this is going to be new 2D of points. And we'll call it n-ary is going to be a Bezier of points, and interpolator is lerp2, right? Okay. So now let us say yeah, I guess that's fine. Sample n-ary. Okay, so that's an equivalence test. We don't need that. and it's going to fail. It passed. Let's see what happens at 1. It passed. Okay. Why am I getting something so weird on our screen then, is what I'm wondering. Interesting. So the question is, do we just need to rebuild? There's some like odd things probably going on with running this as a separate example rather than the runner. Okay, so now it's actually working. It must have been that coefficient and it just didn't get recompiled. But it's nice to have a test. The matrix form should be equivalent to the de Castillo method. Okay. That's good. And all right, we got 10 minutes left. Maybe we could do, now that we have kind of a formula, right? Maybe we could do B-splines. And then after the stream, NNB, thank you for being here, I will look at your PR to easings. And hopefully what I'll do is I'll get the rest of this matrix library built out enough that I can release at 0.1, and then I can bump this version and release at 0.2. And then we can move on. So the goal then for next week would be, assuming I'm able to stream at the same time. I might be able to stream at a different time, but the goal for next week would be to make ways to take a sequence of points where there's at least 4 and construct sequences of splines. And then do what, like, for uniform splines, right? Then do what Freya talked about in her video, where you take the integer part of the t value to tell you which curve to sample. And then you could sample sequences of curves, so actual splines and not just curves. That would be cool. Okay, so yeah, let's do, I don't know, they're just called B. I hate that. Oh, all right. We're gonna need a lot of the same things up here. So let's copy that over to B. It's the worst name. We're not gonna need lerp. But let's make B spline, and we're just gonna call it B spline rather than B. And let's look at the formulation of that. I think that it's basically going to be catmull-rom, but with a different characteristic. So we can copy this business. And we'll say B-spline of A. Okay. So we need to do the same constructors as we did for, say, catmull-rom. I guess I could make it opaque. The interesting thing is now we don't need it. We don't need catmull-rom to be opaque. These are just convenience constructors. As long as you meet these contracts, it's fine for it to not be opaque. Okay. So really this is just about making convenience constructors. And this will be B-spline. And again, the same thing applies. Constructs a 3D B-spline. Constructs a 2D B-spline. Okay. So now we need to go back to our little document, and this is elsewhere. We can find it on Wikipedia, but it's easier to do here. And we'll write the sample function. And the thing is, it's basically exactly the same. But what we have is a factor, and maybe what we could do later is make a generic sampling, if we want to, that takes, the things you extract out of these and does all of this, and you put in what is the initial scale factor, what's the characteristic matrix, how do you do scaling the items, how do you do summing the items, and that would be pretty awesome. Okay, so we need to import vec4f, and we need to make the characteristic. All right. And my apologies. 1, -3, 3, -1. We'll put make them floats in a minute. 4, 0, -6, 3. 0, -6, 3. 1, 3, 3, -3. And then 0, 0, 0, 1. Isn't it really interesting that this is the way that you can define any of these parametric cubic curves? I think that's really intriguing. And then, so now this is the characteristic, but we have 1/6. So this is 1.0 divided by 6.0. I think that that's the easier way to express it than trying to, yeah. Okay. Pretty awesome. Okay. Okay, samples any B-spline. Yeah, and I think it's important to say that this is usually. There's no reason you can't go beyond that. It's just that if you're concerned with the domain within which these points are very relevant, obviously if you get out here to the right, you go beyond 1, the B3 will gradually decrease and B4 will go up and until it reaches 1. Or maybe beyond 1. And then, B2 will be going down and eventually reach 0. B1 will also eventually reach 0. But B3 is probably like on a trajectory like that. And the inverse is true for if you go below 0. So it's really, you're mostly concerned with 0 to 1 in all of these. But those basis functions can tell you kind of what will happen when you go beyond this range, right? Or this domain. Okay. Pretty cool. Okay, so maybe we can plot the B-spline with the same things, and then we can call it for the day. Okay, so we need to duplicate basically what was in here. And we're going to say splines B. And we'll call it B new 2D. And let me just go call that B. Probably not the best name for module, but oops. So this doesn't take points. What do we do in Catmull-Rom? Okay, I just copied pasta. It's fine. We'll do it like that. Okay, now it should compile, and now the question is, how do we add it to our showcase? So let's say B-spline. And import showcase B. Okay. And we'll start with Catmull-Rom again, that's fine. Okay, so if we're Bezier, we want to go to B-spline. Catmull-Rom, we go to Bezier. If we're B-spline, we go to Catmull-Rom. Okay, and then down here in the view, add missing patterns, and we'll say B.showcase. Easy enough. And Luster's not complaining at us. So let us have a look back at our showcase. Okay, so there's Catmull-Rom, there's Bezier, and there's B-spline. Yeah, no, that it doesn't necessarily go through the point, right? But the smoothness there is interesting. Cool. All right. And yes, I agree with you, NB. We'll make more points. But what I want to do is come up with an API that lets you make sequences of splines, sequences of curves. And maybe we put it here, and like you supply the, hey, here's the constructor function for every 4 points, that sort of thing. That would be good. Okay. Feels like a good place to stop. So let's make, let's just add the whole directory here. And I'm going to say Work in progress using matrix form. Pending release of the matrix library. I'm going to go ahead and push that, even though it's going to fail. The test, the GitHub workflow is not going to pass because I don't have it. Yep. And let's actually do that. Okay. So now I need to make a GitHub project for this, and I need to decide on a name for it. So when I get that settled, it might be. I'm thinking right now it's gonna be like the Gleam, the ezines, right? Ezines Gleam. It's gonna be Matrix Gleam. And I think that's probably a good thing to do. All right. See you all next time. Thank you so much. Have a great Sunday.